When you watch a modern rocket tear through the sky on a thunderous column of fire, what you are really witnessing is not just a machine climbing into space, but the peak of a very old idea. Using fire to push something forward. It captures attention instantly because it violates everyday intuition. An object the size of a building overcomes Earth's gravity, something that for most of human history felt impossible. That sense of impossibility is the first hook. Before you understand how it works, you are already emotionally invested, because a rocket represents the outer edge of human ambition, leaving our home planet behind. But this story does not begin on futuristic launch pads or inside high-tech space centers. It begins almost by accident with people who had no intention of reaching space at all. More than 1,000 years ago in ancient China, alchemists were searching for eternal life. They mixed substances like sulfur, charcoal, and saltpeter, hoping to create gold or reverse aging. Instead, they discovered something far more explosive, a black, unstable powder that offered no immortality, but released tremendous force when ignited. Without realizing it, they had created the first rocket fuel in history. This is the first major turn in the narrative. Humanity often advances not through perfect planning, but through curious mistakes and unexpected discoveries. Rather than building guns, the Chinese turned this mixture into something else entirely. Bamboo tubes packed with gunpowder attached to arrows that propelled themselves forward when lit. These fire arrows were not just weapons, they were working demonstrations of a fundamental physical principle. By sealing one end of the tube and leaving the other open, hot gases escaped violently, pushing the arrow in the opposite direction. Centuries before Isaac Newton put this into words, engineers were already applying the idea that every action has an equal and opposite reaction. This is where the audience gets that powerful mental click. The laws of physics we learn today were once discovered through raw experimentation and intuition. These early rockets were unstable, unpredictable, and dangerous, but they worked, and they worked well enough for someone to push the idea further. During the Ming Dynasty, rocket technology matured. Multi-stage systems appeared, something that sounds thoroughly modern, but existed hundreds of years ago. One of the most impressive examples was known as the Fire Dragon. It was massive for its time, built around a bamboo core, topped with a carved wooden dragon head, and fitted with multiple rocket engines. After the initial boost, a second set of engines ignited automatically, extending range and accuracy. At the final stage, a cluster of arrows shot out of the dragon's mouth. Here, the tension rises because we realize something unsettling. Many ideas we associate with the space age were already present in ancient military technology. Despite this ingenuity, there was a hard limit. Gunpowder was inefficient, inconsistent, and impossible to control with precision. To truly escape Earth's atmosphere, rocket technology needed a radical leap forward. That leap would not come from a launch pad, but from a notebook. In the early 20th century, a quiet Russian schoolteacher named Konstantin Tsiolkovsky solved the problem mathematically. He proved that spaceflight was possible, but only with the liquid-fueled engines capable of extremely high exhaust velocities. This is another powerful hook. Before engineering came mathematics, before metal came imagination. Tsiolkovsky described concepts that sounded almost absurd for his time. Multi-stage rockets, gyroscopic guidance, and the use of liquid hydrogen and liquid oxygen as propellants. The challenge was enormous. Liquefying oxygen required cryogenic temperatures far beyond what early technology could easily achieve. But the world was changing fast. Electricity was spreading, industry was accelerating, and what once seemed impossible slowly became achievable. The theory was ready. All that was missing was someone brave enough to build it. That person was Robert Goddard. In 1926, in a field in Massachusetts, he launched the first liquid-fueled rocket in history. It flew for only a few seconds and reached a modest altitude, but it changed everything. For the first time, rockets were no longer limited to burning solid fuel in an uncontrolled way. Goddard introduced critical innovations like regenerative cooling, where fuel circulates through the engine walls to prevent them from melting, and gyroscopic stabilization for control. Each innovation solved a deadly problem. Together, they formed the foundation of modern rocketry. Yet, in his lifetime, Goddard was mocked and dismissed as a dreamer. This part of the story builds emotional tension. A visionary ignored, whose ideas would only be celebrated after his death. Meanwhile, in Europe, a new generation of engineers was inspired by these breakthroughs. One of them was Wernher von Braun. His work led to the development of the V-2 rocket during World War II. It became the first human-made object to reach space. The V-2 introduced advanced fuel pumps, cooling systems, and guidance mechanisms, producing enough thrust to escape Earth's gravity. But this achievement came with a dark shadow. The same technology that opened the door to space was used as a weapon of war. Here, the narrative reaches a moral conflict. Scientific progress and ethical consequences are inseparable. After the war, the world split in two, and rockets became the centerpiece of a global rivalry. The Soviet Union made a decisive breakthrough with the R-7 rocket, the first capable of placing objects into orbit. Instead of a single massive engine, Soviet engineers used clusters of smaller engines, increasing stability and reliability. This design launched the first satellite and carried the first human into space. Every success was not just scientific, but symbolic. The tension of the Cold War pushed rocket technology forward at an unprecedented pace. The United States responded with one of the most ambitious engineering projects in history, the Saturn V. At its core was the F-1 engine, the most powerful rocket engine ever flown. Early tests were catastrophic. Violent combustion instabilities tore engines apart, suggesting that engineers had crossed a physical limit. But the solution was unexpected. The problem was not chemistry or mechanics, but acoustics. By carefully shaping internal structures to control vibrations, engineers transformed destructive chaos into controlled power. This moment represents the technological climax of the story. Humanity mastering forces that once seemed uncontrollable to reach the moon. After Apollo, the focus shifted again. NASA pursued reusability with the space shuttle. Its RS-25 engines had to operate at sea level and in the vacuum of space, throttle precisely, and fly repeatedly. They became marvels of efficiency and reliability. But even this was not the end of the story. Decades later, a private company decided to rethink everything. SpaceX set out to build engines that were powerful, efficient, reusable, and cheap enough for mass production. The result was the Raptor engine, using methane fuel and a full flow-stage combustion cycle. It combined the raw power of the past with the efficiency of modern engineering, designed not just to reach orbit, but to enable interplanetary travel. And here comes the final philosophical turn. Despite all the sensors, computers, and advanced materials, rocket engines are still doing something incredibly primitive. They are burning fuel and throwing it backward to move forward. The difference is that now we control this fire with extraordinary precision. The history of rocket engines is not just a story about machines. It is a story about curiosity, accidents, ambition, war, dreams, and persistence. It proves that simple ideas, pursued relentlessly over centuries, can carry us beyond our planet. If you have followed this journey to the end, take a moment and think about what comes next. Nuclear propulsion, electric engines, solar sails? History tells us there is always another leap waiting to happen. And that is why I want to hear from you. Which moment in the evolution of rocket engines impressed you the most? The accidental discovery? The ignored genius? The space race? Or the dream of reaching other planets? Leave a comment and join the discussion. If this story made you look at the sky a little differently, subscribe to the channel, hit the like button, and stay with us. As long as there is fire, curiosity, and the desire to go further, this story is far from over.